Good afternoon, CS109. How are you guys doing today? Oh my God, it's so good to be back. As you guys know, on Sunday night, I got very, very sick, and I continue to be sick into Monday. It wasn't COVID. It wasn't the flu. It was something I picked up from my daughter, so it goes. But I feel so much better now, and thank you to our wonderful TA teams. On Monday morning, I thought we were going to cancel class. I was just like, I'm not feeling right. Let's see how I feel. And then by Monday midday, I knew there was no chance I could teach. So around that time, I got in touch with the TA teams, and there's one TA, I've got some time, Chris. I think I can do this. So we were going to cancel class, and we were just going to not be able to see that material, and the whole class would be pushed back. And fantastic. Man, we have such a wonderful TA team. I appreciate all of them. So quick round of applause for our wonderful TAs. Someone looked at our course calendar like, I have never seen so many office hours from a class, and that's because our TAs are doing like the extra mile. I've seen it in lots of places where they're just staying late to help students on the forum, the nice messages they post. We have a really special team, and you guys make my job so wonderful. Good people to work with. I have so many things to talk about before we jump into material. The first one is I just want to make sure we're grounded in where we are. We talked about counting theory, we talked about core probability, we talked about random variables. We put lots of random variables together, and now we're in a section of CS109 where we talk about the beautiful theories that everyone should probably know. We learned about beta distributions, and I hope you guys now agree everyone really should know about beta distributions. And then we talked about adding random variables, how that led to central limit theorem, and how the central limit theorem really inspired really nice understanding of sampling. And today we're going to take that a step further, and we're going to be learning about bootstrapping, and on Friday we'll talk about algorithmic analysis. I did also want to mention the midterm. Because I was sick on Monday, I didn't get to talk that much about it, and there's not much more to add. One small thing to add, you guys have already seen the distribution, but have you noticed how the distribution really looks like it's beta distributed? Peculiar. That's not that important right now. There was this small misconception of, oh man, if I got 50 on the midterm, does that mean I've basically failed CS109? And the answer is no. I asked a pretty hard midterm with very real world problems. Like all those problems actually had correspondence to the real world. If you were in the real world, someone might give you that problem, and if you solved it, it would be a big deal. So if you could solve all 7 of those problems, that's amazing, fantastic. Like just keep doing your thing. And if you could solve all but one of those problems, man, that's amazing too. And if you miss 2 problems, that means that you could do 5 out of 7 or 4 out of 6 real world problems. That's really rocking. You guys are making good progress. And there's a lot of different versions of, you guys have really impressed me as a class to say. And I did want to drive home I'll get to this in a second. I did want to drive home this point. And you guys know probability well enough to understand what I'm trying to say here. 3 random variables. G is your grade in the class, S is the score you got in the midterm. Why do I keep hitting the wrong button? And D is the difficulty of the midterm. And what am I trying to say with this equation? Probability of your grade taking on the value little g is equal to the probability of grade taking on the value little g given D equals D. What am I trying to say here? Yes?
Independent of how difficult the midterm is.
Yeah, exactly. All I care about is what you guys know. I ask real world problems that are complicated, to give you the scenario. But asking a harder exam should not change your belief in the difficulty, and that was a hard exam. And then there's one other policy that I need you guys to know about, which is that I really appreciate that exams are a bit stochastic, and sometimes people walk into the midterm and maybe they weren't as prepared. Did you have a bad midterm? That's fine. Grade's still in your control for lots of reasons. One is that problem sets count for a lot. One is that there's this optional contest, which we'll talk about in a second. But also, I have a policy of always looking at people's final exam scores. And if I look at your final exam score, I look at your midterm score, and I was like, that's pretty substantial improvement between the two. I'll recognize that the final exam score is cumulative. So you've showed me that you learned. I don't necessarily care what you knew at the mid-quarter. I care about what you know at the end. So if you use this midterm as a diagnostic and you can improve and you can show that improvement in the final, you don't have to get an A+ in the final for this to kick in. But if you can show improvement, then I always recognize that because I appreciate people working hard and people trying to improve themselves. What a beautiful thing. Okay, another quick announcement. If you want to improve yourself, one of the cool things you could do is go check out the CS109 problem set party. You go to the PSET app, and at 7:15 there'll be a little notification that goes out. If you click on it, we'll try and put you with like a group of people or another person in class, and you guys can just like either have a social moment, or you can teach each other something, or you can just like commiserate about something. All's fair. And this is not that important, but I asked our AI overlords, what do students at Stanford learn together at a PSET party look like? And this is what they gave me back. And I'm not going to interpret it, but I just thought that was interesting. Okay, and then finally, as you guys know, one of the reasons that in CS109 the grade's still under your control is because there's lots of ways of showing us that you know probability. One of the ways is to express what you've learned in probability about something you care about in your own life. And that's one of my favorite ways that you could express it. Totally optional, and optional in the sense of the word that if you don't do it, you'll get the same grade as if it didn't exist. But if you do it, this contest, what a cool thing. All the details on the website. Okay, we're gonna learn something really, really, really cool. But I need to motivate it. I need to give you, could you grab me a glass of water? Okay, thanks. I guess I haven't been talking for a couple days. I want to motivate it. By the end of today's class, you should be able to answer a problem that looks like this. And at first, it doesn't seem that important, but let me tell you, this is one of the more profound questions you can ask in science. Okay, imagine you have two different learning contexts and you want to figure out, is one better than the other? So you have a certain number of people do learning context A, and you have a certain number of people do learning context B. One of the first things you do is for each person you measure their outcomes, and then you take the mean. And you say in learning context 1, the mean was 3.1, and learning context 2, the mean was 2.4. And then I ask you this question. I says, is this difference in means of 0.7 meaningful? And how confident are you in the claim that, how confident are you in the claim that group A is in fact 0.7 points better than group B? It doesn't seem that meaningful. It seems nice to know, right? Like you should be able to do that, but it doesn't seem so critical. But the reason it's so critical is this is the classic science test. If you ever want to write a science paper in almost any discipline, whenever you make a claim, you have to talk about the probability of your confidence in your claim, a thing called a p-value. So if you want to do biology or chemistry or physics or computer science and you want to do maybe computational education, anything in that space, if you did an experiment and you came up with a result and that result has a claim, you have to associate a probability with it. And today, not only will you be able to associate a probability with this most classic sort of result of differences in means, you should be able to talk about a probability of any claim that you could make in a scientific paper. How cool does that sound? Who wants to know how to do a p-value? Yeah, okay, bear with me because we're gonna get there by the end of today's class. And actually, we'll get there by, the middle of today's class. But first, a little bit of review. This whole story starts with the central limit theorem. The central limit theorem, what a beautiful thing. If you take different IID random variables and you sum them up, no matter what IID random variables they are, as long as n is large enough, it will always converge to a normal. The sum will always converge to a normal. And there's another version of this, which means if you take that sum and multiply by 1 over m, aka you take the average of IID random variables is always normally distributed. And that is a powerful thing that showed up in the world of sampling. Remember sampling? You have a population, but you can't get numbers from every single person in your population, so you talk to a subsample of them. And numerically and in notation, we'll represent our sample as a list of random variables. We'll think of them all as IID. They're independent, but they're pulled from the distribution of the population. So if this green is the population distribution, we're imagining we're getting like 200 samples from this population distribution. Because of the central limit theorem, some beautiful things come out. First of all, if you have a sample, the mean of your sample is unsurprisingly take all of them, add them up, divide by n. We learned that a long time ago in like 6th grade. What you might not have learned about in 6th grade though, is if you want to know the variance of your sample, you can estimate that, and it looks so much like the equation for variance, except for this cheeky n-1. It's so cheeky, go check out lecture to learn why there is that n-1. But basically, if you don't have that n-1, because you're estimating because you're estimating the sample mean, you will get this wrong. You will have a biased estimate. And then finally, this very CS109 insight. Sample mean is a random variable. And that makes sense. Every time you take a sample and get a number, it's going to be different. So even though you get a value, it'll take on different numbers. Probabilistically, it's a random variable. And because of that, you can ask questions like, what's the standard deviation? And I've told you nothing about the underlying distribution. And even though I've told you nothing about the underlying distribution, I can tell you how you could calculate the standard deviation of its mean. That's insane. It all comes from the central limit theorem. Because the central limit theorem tells us that the variance of the average of IID random variables is a particular square root of the true variance divided by how many things you've added up. Then we can know what is the variance of the standard deviation of the sample mean. If any of this is new, certainly review Monday's lecture. Oh, there is this really cool example that did where he actually took all the times it took people to complete the problem set problems, and then for each one we calculated the standard mean and also the standard deviation of the standard deviation of the sample mean. I want to just point out one more thing. We're talking about statistics here, right? Like you had a sample, and the two statistics that we could talk about, particularly for the sample, is what's the mean of the sample? We could talk about the variance, but often we write error bars, which is the standard error, and standard error is just the standard deviation of the sample mean. And so the standard deviation sample mean, that's what error bars are. Those are just statistics. So if you took any one number, if you expand it out, there's a whole distribution underlying. I did want to just highlight that we're talking about statistics, not about the underlying distribution. Am I making sense? Okay, anyone curious about what that distribution is? This is how long it took people to do the medical diagnostic problem on the problem set, and you're like, we all feel for these people, respect. But what distribution do you guys think this is? You guys curious? I'm curious too. I don't think anyone knows. I think it might be airline, which is the sum of exponentials. So it's like there's 5 concepts you need, and it's the amount of time to get concept 1 plus the amount of time to get, who knows, could be airline. Could be Gumbel, which is the max of different random variables. We could talk about this offline. It's really not important right now. But the important part is to keep reinforcing in your minds the difference between a statistic about a random variable and the underlying distribution. Lots of people care about statistics, but if you could walk out of CS109 caring a little bit more about the underlying distribution, my heart would be so filled. Oh yeah, okay, airline versus Gumbel, not that important right now. But what about Bhutan? On Monday, we left with this deep mystery. We were making a report for the government of Bhutan, and the government of Bhutan had asked us, can you report on the happiness of our people? So we took a sample of 200 people. We reported the average happiness, and then we reported the sample, the variance of the sample that we got of the 200 people. And we used this equation where you use n-1 to make sure it was an unbiased estimate. Fantastic. And then we showed it back to the king of Bhutan, and the king of Bhutan's like, what are you doing? There's no error bars there. We're like, oh yeah, of course. So Monday's class, we're like, we're going to add some error bars. And first of all, adding error bars to this estimate of the mean was really straightforward. We would just use the fact that a mean comes from the central limit theorem. We know it's going to be Gaussian. We know that its particular variance is going to be s squared divided by n. And the standard deviation of our estimate should be this value. We've got error bars. And we go to the king of Bhutan, we're like, we got error bars. And the king of Bhutan's like, no you don't, you have error bars on one of your statistics. What about your error bars here? Uh-oh. And you're like, huh, well, we got these error bars because x bar was the sum, or is the average of IID random variables. Central limit kicked in, we could know its variance. And you're like, is this the sum of IID random variables? And you're like, ooh, I don't know. You're like squaring things, and then I'm not sure this is actually going to turn out to be Gaussian. It turns out, if you went down this path and tried to figure out eventually if central limit theorem applies here, it turns out it doesn't. You can't just use our old trick. So what I'm going to teach you is a general trick. Anytime somebody wants you to know about a distribution of statistic, anytime somebody wants you to know a p-value for science hypothesis, we're going to use this one most beautiful randomized algorithm. Which is called bootstrapping. And it's one of my favorite randomized algorithms. I think it would show up in every probability class if people knew how to program, because it is such a powerful tool for understanding the underlying probabilities, particularly from data. I think every data science class would teach it, every probability class would teach it, but not everybody knows Python the way that you guys do. Bootstrapping is going to be an algorithm, and it's going to solve two separate problems. If you wanted to know about a distribution of statistics, like you want to know what's the variance of my of my estimate standard deviation, you could know that for any statistic. And the generalization of that is you can calculate these most important things for science called p-values. And it's going to take advantage of the fact that you have computers. And if you ask your computers to work hard, they can figure out these p-values for you. And it's just going to take a little bit of probability theory to get there. So let's go back to that challenge we had with the King of Bhutan. The King of Bhutan said, estimate the variance of happiness in my country. And we gave the King of Bhutan a number. We said the variance of happiness was, I'm going to make this up because I can't remember, but 420 or something like that. Standard deviation would be the square root. And the King of Bhutan is, what is the variance of your estimate? What are those error bars, or the standard deviation of your estimate? So you want to know standard deviation so you could give these error bars, but that was hard to do, and we don't have a solution. I'm going to give you a simpler way to come up with the solution. I'm going to tell you the happiness of every person in Bhutan. That's right. I'm going to let us cheat a little bit. And you're like, once I know that, do I even need to know the standard deviation of my estimate? And you're like, no, you wouldn't need it. We're cheating, because obviously we're not going to talk to every person in Bhutan. But imagine we had. We've talked to every single person in Bhutan. And after we talk to every single person in Bhutan, what do we have? You could say we have a histogram. And on the x-axis is people's happiness values, which are obviously numbers between like 1 and 10. And on the y-axis, you could think of this as a histogram. But better yet, if you normalized it, this should be the probability mass function. So you should say the probability that the happiness of some person equals little h, where this x-axis is little h. So my question for you is, I give you the full probability mass function of happiness in Bhutan. And now I ask you this question. Can you tell me how bad was my estimate, 420, for variance? And particularly, I got this estimate after talking to 200 people. That 200 is important. You know, if I got my estimate after talking to 10,000 people, maybe I should be pretty confident. But after talking to 200 people, I should have some room for doubt in my number. This is a hard question to think about. But I want you to figure it out, because if you could figure it out, then the whole rest of this lecture is going to flow like water in a beautiful canyon. So let's see if we can figure it out. How could you estimate how bad your measure of sample variance was if I gave you access to everybody in Bhutan? Yes, question?
Take the expected value of the square difference, or?
I'm going to let you guys, I don't want the answer yet. You guys are going to think about it. That was a good proposal answer, but think about it. What would you do? There's other ideas. And think about, you can use computers as much as you want. Imagine you have a laptop which is as powerful as your, I don't know, smartwatch. Okay. Good? Fantastic. Think about it. Let's see if we can figure this out. Let's invent some cool stuff. So how are we going to get this estimate? If people have questions, if there's something unclear, just raise your hand. One of the TAs will come and answer your question. Okay, yeah, go talk about it with the person next to you. Okay, thank you. It passed. Thanks, man. Appreciate it. If you have any questions, raise your hand. We'll come answer. Okay. Let's do this. And if I could focus everybody on one part of today's lecture, it would be this one. Because if we can really crack this and understand what we're doing here, I appreciate the why is not as deeply motivated, but if you can understand the mechanism, then we'll be able to follow the rest of the lecture. So let's make sure we take the time to get this right. Just to make sure we're all on the same page. Variance is the measure of spread. So the king of Bhutan doesn't just want to know average happiness. They want a statistic of how much happiness spreads. Because if that's low, then everyone has close to the average. But if it's high, then you'll have some really happy people and some really unhappy people. So that measure of spread is something the king of Bhutan wanted. But because we only talked to 200 people, we don't have the variance. We have a thing called the sample variance, which is our estimate of spread based off of just talking to 200 people. It's not going to be the right number. We only talked to 200 people. And as such, we want to know how much this number would have changed if we talked to a different 200 people. We want some measure of how much this number is changing. And we're getting meta. I appreciate how meta we've gotten. You have variance, and now we're asking for a variance of the variance, like, whew. Or if you're into square roots, standard deviation, the standard deviation, incredible. Questions, clarifications, let's talk about things before we talk about ideas. Yes?
Yeah, so this is the meta part that I don't fully get, I think. So when you say the standard deviation of the sample variance, what are we measuring the spread around? Are we measuring the spread around a mean?
Yes, this should be around the mean of the sample variance. This sample variance is an unbiased estimate because we got that n-1 in there. It turns out whatever you get for sample variance is what we call the mean of the sample variance. So it's around the number you got. So if the number you got when calculating sample variance was 420, this will be the standard deviation around that 420. Long story short. Does that answer the question? Awesome. Other questions? Yes?
Is our sample variance, is that considered a random variable?
Yeah, it is. That's a really good point. So it's a random variable. So underneath the hood, it's going to have a distribution. What does that distribution look like? Have you guys ever seen a distribution of variances? Oh my God, today is a first in your lives. Can I tell you what it looks like? I didn't plan to do this, but I want to. I'd like to tell you what. You've never seen a distribution of variances? Oh man. Okay, well first of all, what's a distribution of means look like? It's Gaussian, because of the central limit theorem. Distribution of variances? It depends what the variance is. Sometimes it looks like this. Sometimes it looks like this. It can depend. But notice a big difference between means and variances. Means can be negative, variances can never be negative. This is not Gaussian. But anyways, you asked the good question and then I went on a total tirade. Is sample variance this thing a random variable? You bet it is. And it's got a distribution. We just never saw it before today. Yeah?
At the beginning of class, you said that the way that we worked out the means variance doesn't work for the way that we work out the variances variance. Can you clarify that?
Yeah, this is your sample mean, and this is its distribution. If you took 200 different people, you would get a different sample mean. It will vary around what number you calculated, and it's going to be a Gaussian. Like if you played 10,000 times the game of getting 200 people and getting their sample means and plotted it, you would get a Gaussian. Because of the central limit theorem. Because of the central limit theorem, we know exactly what's the variance of this Gaussian. That's not a Gaussian. Central limit theorem is not our friend today. Well, it's always our friend. It's just not the friend that can solve our problem. Okay, one more question. I do need to jump into things.
If you use some sort of a theorem involving chi-squared, would you be able to avoid using Bootstrap to answer this question?
I want to avoid that because there are shortcuts that people have. So, okay, let me just generalize this question. There are shortcuts to several of the questions I'm going to ask you today, where somebody might have done some math to propose an answer to just that question. What I'd like to teach you today is a way to answer all of the questions, so a much more general method. So yes, there are ways you can circumvent Bootstrap basically for any problem. But Bootstrap is like your Swiss Army knife tool. And if you can master this tool, then all these problems, you don't have to learn a chi-square test or a t test or all these different mini tests. You can just use the power of Python and your understanding of probability. It's a beautiful thing. It's like the most CS109 thing in the world. I'm so excited. Okay. So now we know what we're doing. How could we do it? And I am looking for pretty simple ideas. So if you had access to all of Bhutan's happiness values, my idea is there some way you could possibly see the distribution of your sample variance? Whoa. Insanity. Not possible. Maybe it is possible. Yeah.
Can you like sample your sample variances and get a bunch of them?
You could repeat 10,000 times. Let's start with that. Okay, so yes, we're going to repeat 10,000 times. What are we going to do 10,000 times, though? Okay, an idea?
From that.
And then, because we have the whole distribution, we could just recreate talking to 200 people. I mean, we're trying to understand how wrong we were with 200 people, so we should take 200 when we're trying to understand this. So we're going to pull 200 random people.
And calculate the sample variance of that sample.
Okay, and then we calculate sample variance. We're using that very nice formula we had from Monday's class. And we've done this 10,000 times. That's going to give us 10,000 different estimates for sample variance. Guess what happens if you took all those 10,000 things and made them into a histogram? You get to see your own standard, the distribution of variance that would come from talking to 200 people. Whew, fantastic. That's on fire. That's awesome. So, does everyone, I want to pause here. This would work, but we're missing one step. How do we then get the standard deviation of sample variance? At this point, we've got our whole distribution from 10,000 times of repeating my experiment. After repeating my experiment 10,000 times, every single time I got a value, and if you histogrammed it, you would get the whole distribution of sample variance. Maybe when you talk to 200 people, you got this number. Maybe when you talk to 200 people, you got this number. If you got crazy unlucky, you might get this number, but the probability will be governed by the distribution. Once I have the whole distribution, it should be easy to get a statistic like standard deviation. Once you do this, you have the whole distribution, and once you have the whole distribution, you can just calculate standard deviation. Man, that's crazy. Like, I really appreciate that I have pushed us all. I made us think about standard deviation of variance. This is insane. But I want to pause and see if there's what's confusing about this here? Because if it's confusing to you, it's confusing to somebody else. Yes?
I'm curious about the value of, like, when you do one of those loops where you take a 200-person example, is the value of the random variance a random variable, a value in itself, or a distribution in itself? Because I know they all add up to a distribution.
It's a sample, and the sample is interesting. We often write it as a random variable, but it will be a number when you calculate it. Like when you run this loop in your computer, you'll get a number. But if I were to write this in an equation, I'd probably say like, sample 1. Then you can say sample 2. But this time it's a sample of your sample variance. But does that make sense? So they will be numbers. Like when you run this in your computer, you're going to get 10,000 numbers.
So it's 10,000 different values.
And they're going to be IID pulls from your sample variance. Okay. You get 10,000 IID pulls from your sample variance.
So you're basically estimating the PMF of S squared. So that is.
That's it. Yeah, so exactly. We're estimating the probability mass function of S squared, and that is giving us all the information we want to know about S squared. Yes, an idea.
Why would it not be a normal distribution then if it's IID?
Good question. Not everything that's IID is normal. Only things that are added together, like if you add up IID random variables, that's normal. If you average IID random variables, that's normal. But the equation for standard variance doesn't lead to something that's normal. And one thing I could also point out too is that variances can't be negative. And normal distributions have no limits on what values they can take on. Yes?
From these 10,000 variances, how do you calculate the standard deviation?
So once you have 10,000 things, you've got this histogram, and then you can use your classic variance from the midterm equation where you just take expectation of x squared divided by expectation of x squared. You can square root it. Or you can use your friend Python and say like np.variance, and then you just put it in your samples and it will give you the variance.
Why does it matter that we know the true distribution if we're just pulling samples anyway?
Okay, but let me be clear about what we've done so far. If I gave you access to every person in Bhutan, we can now talk about how wrong we were when you canceled the sample variance. And we could talk about that by expressing the full distribution of sample variance. But your question is, why do we need access to everybody in Bhutan? And it's important because we don't have access to everybody in Bhutan. That kind of breaks the whole scenario. We'd like to be able to do this with only access to our 200 people. I'll take one more question before I jump into the next part.
So, is there maybe like just an established like how much you have to sample a population for like typically good enough?
No. We can talk about this offline, but that's, it depends a little bit. Okay, so where we are is 10,000 times, take a mock sample. Talk to a mock 200 people, calculate the sample variance. Now you've repeated your experiment 10,000 times, and because you've repeated 10,000 times, you can think about how wrong any one experiment is. Because you can think about, how different it could be from the true variance. So, here's my crazy, crazy claim. So you guys are halfway through this wonderfully complicated and beautiful idea called the bootstrap. So what we've talked about is the first idea, that if you want to know about some statistics, just repeat many times and recreate the experiment as good as you can. Calculate your statistic, then you'll have 10,000 versions of it, and that's the full distribution. That's the first half. The second half is a bit of a leap of faith. We don't have access to everybody in Bhutan. What we have access to is fewer people. Imagine, say, we had access to 1, 2, 3, 4, 5, 6, 7, 8 people. If I histogram this and then normalized it, we can think of this as an estimate of probability mass function. What's my estimate at this point that somebody's happiness is 90? Well, I saw 1 out of 8 people with 90, so maybe there's 10 here. Anyways, I saw close to 1 out of 10% of people with 90 happiness, so I could estimate that's probably somebody has happiness 90. Never saw somebody with happiness 91, so that's not possible. I saw 2 people with happiness 92, just 1 person with 93, and I saw a whole bunch of 3 people with happiness 94. So this sample, we can represent it as a histogram, and that histogram has a nice analogy with a probability mass function. Because a normalized histogram is a pretty nice approximation of the probability mass function from your data. Somebody at Stanford, not too long ago, I don't know what they were doing, but they had this wacky idea. They said, if I don't know all the people's happiness in Bhutan and all I've got are these samples, then this probability mass function is a pretty good approximation of the true probability mass function of all the happiness of people in Bhutan. And people are like, what? That's crazy. Yeah, he's like, the distribution you get from the histogram of your sample is a pretty good estimate for the true underlying distribution. Crazy. The first time I saw that, I was like, nope, that's not right. Turns out it was right, and this guy got all these awards for figuring this out. But if you go back to our true distribution of happiness, if we see in 100 samples, 6 people with happiness 2, what's our best estimate for the probability that happiness equals 2? Well, according to the very first definition we had of probability, we had 100 samples, and let's say we got 7 people with happiness equal to 2. Therefore, our best estimate for the probability that happiness equals 2 is about 7 over 100. As 100 increases, this will be a better estimate, but based on this underlying assumption, it's not that crazy an extension to say, well, if you extend this to happiness equals 1, happiness equals 2, happiness equals 3, you get to the conclusion that your sample's pretty good estimate of the true underlying probabilities. And then he put those 2 things together, because now we've got some peanut butter and we got some jelly, and we're going to make a delicious sandwich. So what's the peanut butter? It's that we could estimate our distribution of something like sample variance by repeating a whole bunch of experiments. And now that jelly is, if you only have 200 people, pretend that's all of Bhutan. Consider that the probability mass function. And when you get 200 more people, you're going to pull from that probability mass function. From the original 200 people. Insane. Let's make that a little bit more graphic. This leads to the bootstrap. This is our beautiful peanut butter and jelly sandwich. Bootstrap goes like this. You are going to estimate the probability mass function using a sample. So you start with your 200 people from Bhutan. Step one is take those 200 people and make your histogram, and then estimate your probability mass function from the histogram. Then 10,000 times we're going to do this. Pull 200 people and calculate the statistics we cared about. And then we have 10,000 draws from our statistic. Okay, now, how do you pull 200 people from the probability mass function? I think that's the interesting thing. By the way, for now, let's start thinking about estimating the mean. We know the central limit theorem will tell us the right answer, but this will be a nice warm-up to the bootstrap. We'll then do something more interesting. Here's how you could get the bootstrap to estimate how wrong your mean was. So you estimated mean, you're probably a little wrong. How wrong were you? Here's what the bootstrap says. First of all, you gave me 200 people. The first thing I'm going to do is I'm going to take those 200 people and I'm going to build a probability mass function. It's going to look like this. Here my happiness scores go from 0 to, I don't know, 120. But anyways, you take all your happiness scores, you histogram them, and then you say that, the probability somebody gets 61, it's the number of times I saw 61 divided by the number of samples I had in my data set. Insane? According to this guy at Stanford, not insane. So now we've got a made-up probability mass function, an estimated probability mass function, if you will. And the next thing we're going to do is say, that's Bhutan. That's all the happiness of all the people. And once we have assumed that, and that is an assumption, then 10,000 times, we're going to do this. Draw 200 samples from this probability mass function. Then we're going to recalculate the mean, and then we're going to save it. So let's draw our 200 samples. Recalculate the mean from these 200 samples. So sorry, I squiggled drawing 200 samples, but you get the point, right? You draw 200 samples, they're not exactly the same blue distribution. And you take the mean of those 200 samples, and I'm going to add it to a list of means. I've done my loop once. You guys ready for me to do it again? Next time through the loop, I pull another 200 people from Bhutan. But of course, I don't have all of Bhutan. Instead, I'm going to use my estimated probability mass function. Insane, but beautiful at the same time. And once I do this, then that red is going to be my 200 pulled people. I recalculate a new mean from my 200 pulled people, and I add this to my list. I now have two estimated means. Were the same? No. Each time when I pulled 200 people, I got a different 200 people. So when I took their means, I got different numbers. They were pretty similar, which is a good sign. If they're really different, that's a bad sign for how well we're estimating the mean. If we do this 10,000 times, I'll end up with a list of size 10,000. And the crazy thing about bootstrapping is that it says this is the distribution of means. Cool or what? Okay, of course it's not that cool. Who cares about distribution means? It's cool when it gets to science.
So if your original sample is like only
200, for example, then if you're redrawing a length 200 sample from that sample, is it not everybody in that sample?
Think about it as every time you withdraw, it's with replacement. So it's not just, every time I draw a person from this probability mass function, the probability mass function doesn't change.
Okay.
It's not like one person gets removed. So every time I draw, it's from the same probability mass function. So for example, I could possibly draw 200 people with that happiness. It's unlikely, but possible. Good question, yes?
How confident can we be that this is accurate? Because what if my 200 people I sample, let's say this is to just really unusually happy people that just mess up our whole process?
Yeah, it turns out that there's a lot of proofs that show that this converges very quickly to the right answer. So at the point where you're at 200, it's possible that something out of distribution would happen, but very, very, very unlikely. And people trust this immensely because there's a lot of evidence behind it. Yes?
Is there a minimum amount of people we need to sample? Because I'm like, what if we sample only like 10 people?
I've never seen somebody attempt this when you had fewer than 200 samples to start with. So that's a good question. Well, you probably people have done it with like 100, but I've never needed to. Yes?
Work out a new mean from sampling this original sample, and then you distribute that new mean that you have.
Yeah, every time in the loop, I get brand new people and a brand new mean. So I'll end up with 10,000 brand new means. Yes?
I think I'm gonna follow up the question on like if you had say only 200 people, if you sample 200, it's a survey data set. So I'm really struggling to understand how it replaces itself.
Yes. So let's say there's 5 samples, and I'm going to resample 5 from that. How's that sound? Can we start with that? And then we'll extend to 200. So in my original sample, let's say it's binary. It's zeros and ones. Phew. And in my original sample, I only had 5 people. What am I doing bootstrapping for? Well, anyways, there was 2 people in my original sample who had a 0, and 3 people who had a 1. So I'm going to say 2 out of 5 people had a 0, and 3 out of 5 had a 1. Those are probabilities now. When I pull 5 new people, it's possible that every time I pull a person, it doesn't change this distribution. So now I'm going to draw people. First person I pull is a 0. That could happen, right? I'm going to draw 4 more people. Next person is a 0. That could happen. Next person I draw is a 0. That can happen every time I'm drawing with this constant probability. So there's always a 2/5 chance of a 0. And I could go and I could pull 5 zeros. So even though the original distribution did not have 5 zeros, when I pull 5 times from the imagined probability mass function, I could get 5 zeros. So you could see something that was not in the original distribution. Yes?
If like of the original PMF, one of these happened to be 0, so like wouldn't that 0 carry on to all the rest people you pick? Like you'd never have another 61, for example, if that was 0 in the original PMF.
Sorry. Oh, yes. So if there's some value and you never see a person for that value, what do you do? 2 schools of thoughts. One school of thought says, that's a 0. It's not possible. Didn't see it in 200? Not possible. And there's a Bayesian school of thought, which is like, maybe we can do some Laplace smoothing here, and we can like add in some observations of a thing. So there's people who get really fancy about it. But for now, we're just going to say, yeah, you didn't see it in your sample? Not possible.
After we pulled the second mean in the list, you said it was like, it's a good thing that they were similar to each other. Doesn't it like make sense that they would be similar to each other because we're pulling from the same thing?
Yeah, and in fact, because these are means, not only does it make sense, but we can know everything without even having done the bootstrap. Because the central limit theorem tells us that the distribution means will be Gaussian. And we know that its mean will be expectation of x, and we know that the variance will be equal to the square root of the distribution of the average of IID random variables. So that's going to be the square root of n times sigma. Did I get that right? N times, okay, 51. Central limit theorem says if you average n IID random variables, it will be Gaussian, and its variance will be sigma squared divided by n. And so the average will be Gaussian, and it will follow that distribution. And if you looked over here at slide 51, if you looked at this distribution, it would be Gaussian. And its variance would be the true variance of the random variable, sigma squared divided by n. And then you can ask questions like, what's the probability that your true mean is in the range 81 to 85? But to be clear, after we've done our 10,000 samples experiment, if I wanted to answer the question, what's the probability that the true mean is in the range 81 to 85, how could I do this using my 10,000 means? So to be clear, after bootstrapping, I've got 10,000 versions of the sample mean. How can I answer the question, what is the probability that the actual mean is in the range 81 to 85? I want you to talk about it with the person next to you, but before you do that, ask the person next to you, is there anything confusing about this? If you guys got a good question, keep this wonderful, wonderful conversation going because I've really appreciated all the questions so far. So what's confusing, and then how could you answer this question using your 10,000 samples? Take 40 more seconds. Okay. So as we mentioned, one answer to this is that you could take your underlying knowledge from the beautiful expression of nature that is the central limit theorem that says if you ever average random variables, it will always be distributed as a Gaussian. Amazing. And not just any Gaussian, a Gaussian whose mean is equal to the true mean of the things that you're averaging together, and whose variance is equal to the true variance of the underlying random variable divided by n. Because of that, you can know this distribution just by first estimating the sample variance, divided by n, and then you could know how much that this thing has a spread. You could estimate the expectation of this by just calculating x bar. It's a beautiful thing. And then you could calculate this. But there's an easier way. If we've just bootstrapped, and we have 10,000 samples from this distribution of the sample mean, there's an easier way to answer the question, what's the probability that the mean is range 81 to 85? Did anyone come up with that easier way? Yeah?
Just by counting?
Just by counting, but tell me more.
You just count the ones that are 81 to 85.
Yeah. I want you to guys start seeing lists and imagining probability distributions. Can we start doing that? You see a list anytime in life. You're like going to be in CS109, and they're like, here's a list. And you start seeing probability distributions. It's like, what did Chris do to me? Anyways, if you see a list, especially if there's samples, I want you to see a probability distribution. And then your claim of counting is very good. You said, take this list and say, what percentage of things in this list are in the range that we cared about? And that's a good estimate for the probability that something drawn from this random variable would be in that range. I have so much appreciation for how deep this lecture is going, and I really appreciate how hard you guys are working to follow this. Not easy stuff, but powerful, important stuff that leads to a tool that you'll use for, hopefully, the rest of your scientific lives. Okay, so we've answered this question. I've set the stage. We should be able to do this. I now want to add error bars to this report to Bhutan before we take this and start to do p-values for science. So how do we take this and get standard deviation of this estimate? So we got 400, something close to 450 was our estimate for the variance of happiness in Bhutan, but that estimate was wrong. Bootstrapping tells us how wrong it might have been. Yes?
Why should we trust Bootstrap just as much as the central limit theorem? Do you have like controls to like test how fast the approximation is working? And
yeah, just in like the central limit theorem, how there's both mathematical evidence, people have actually done proofs to show that this converges to the right thing, as there is a lot of empirical evidence. So for both those reasons, we trust the central limit theorem, and for both those reasons, we trust the bootstrap. And we should, let me see if I can pull up some experiments showing you how quickly it converges. Okay. If you wanted to figure out standard error bars for our estimate of variance, we're going to use the exact same algorithm. It's just we're going to replace these two things with variance. In the loop, instead of calculating means, we're going to calculate variances. So we're going to repeat 10,000 times. First, before we repeat 10,000 times, we're going to estimate the probability mass function from our sample. So we took our 200 people, said, that's the distribution of happiness in Bhutan. Then 10,000 times, we pulled 200 new people from that probability mass function. And then this is where it deviates. From these 200 people that we just pulled, don't calculate the mean. We're talking about the distribution of sample variance. So let's calculate the sample variance. And if you calculate the sample variance, we've got an equation for that. Maybe this time you get 472.7. We're going to repeat this 10,000 times. So the next time, we will get 200 different people. And this time when we calculate the sample variance for those 200 people, you'll get a different number. And if you repeat this 10,000 times, you'll have 10,000 different estimates of the sample variance. And when you see a list, what should you think? Okay, let's try that again. When you see a list, what should you think? Yeah, if that is a list of samples, that it should be a probability distribution in your mind. And the way you could get there is you could think list, then go histogram, the normalized histogram. Because of this, first definition of probability, that histogram is going to be a probability mass function. So if you want to see it as a graph, that's how you do your translation, but a list is a distribution. So now we have a distribution. It's not talking about particularly the variance of happiness. It's a distribution of, this is the full distribution of things we could have gotten from our sample variance. Like in one experiment, we could have gotten this number. In a different experiment, we could have gotten this number. In a different experiment, we could have gotten this number. After 20,000 times, this is all the different numbers we think we could have gotten from asking 200 people their happiness and then calculating sample variance. And then if we were to plot it, you would get that whole list would give us a distribution, and you can calculate the standard deviation from this distribution. Insanity. Yes, question?
Well, in the beginning, we talked about the spread around the number that we had originally calculated.
Yes.
So I just wanted to relate that to this sort of, whatever number we're coming out of from this distribution.
So before we did all of this, you could have just taken your sample and calculated the sample variance, and you have one number. So you have the one number, which is the bar that we were putting in our report. And now we have these 10,000 numbers, and that will give us in this case, it'll just give us this error bars for that bar. One thing I would mention, if you took all of these 10,000 samples and you calculate the mean of them, you would get something exceptionally close to that original number you calculated. So when you just took your 200 people and just calculated sample variance, if you took the mean of this distribution, it'd be basically the same because it was an unbiased estimate.
And so we make it an unbiased estimate by doing the division by n minus 1. That I don't understand.
Yes.
How do we, why does the minus 1 make a difference?
Oh, there's a deep, deep answer to that. Let's talk offline because it'll go long. Okay. Craziness. The beautiful part of this is we can now put error bars on our report to the King of Bhutan. I'm going to give us a pedagogical pause. I want people to come ask me questions that are in 2 minutes. Try and crystallize what we've learned so far. And I'm going to leave the bootstrapping algorithm up here. It's a beautiful, powerful thing. It's not that many lines of code, and it's going to let you do some real magic with probability. So take 2 minutes, think about life, ask some questions, come find me, and then we will continue this wonderful conversation. Because it's like we're trying to talk about how bad our estimate when we talk to 200 Bhutanese people. So that's why it should always be 200. If we if you had 10,000, if we had sampled 10,000 people, you'd expect our sample variance, the variance of our estimate would be very small because we talked to so many people that if you talk to 10,000 different people, you probably get a pretty similar number. So it does matter how many people you talk to. That will change you'll change your error bars. No, always the exact same number. Always the exact same number. Good question. Okay.
I'm just a little bit confused on exactly what we were
touched in conversation. I'd like to repeat 2 things that came up in conversation. First of all, I appreciate that I first made you think about sample variance, and then we're measuring the spread of sample variance itself. It's like you're talking about the variance of variance, and then I promised somebody in questions I'll never make you go one level deeper. It'll never be the variance of variance of variance. The other thing is, you know, a really good question is, what are we doing here? Can you just restate what we're doing here? I feel like that's a nice way to come back from the pedagogical pause. People everywhere in life are giving you statistics. And anytime somebody gives you a statistic, they should tell you how wrong they think they are. And in science, this is a must. In the news, it's not always a must, but it really should be. Some statistics, it's easy to know how wrong you are. A sample mean, it's easy to know because of the central limit theorem. But that's very much a special case. Most statistics that get reported to you that are not sample means, there's no good language for talking about how wrong you were. Sample variance is not sample mean. It's just my first example of some statistic that we could be reporting for which there's no good language for talking about how bad your estimate was. And we really want to talk about how bad our estimates were because, as we know from CS109, those who can express how wrong they are make better decisions. And so anytime you see a claim in a newspaper about a statistic, anytime you see a claim in science about statistics, you should always ask yourself, how wrong could they be? And there's lots of things that could lead to this source of error. Like if you only talk to 200 people, you might be pretty wrong. If you talk to 10,000 people, maybe you're less wrong. Maybe I have more confidence in your claim. But you should be able to give me, in the language of probability, how confident you are in your claim. Enter the bootstrap. The bootstrap will allow us to talk about how confident we are in any statistic, even if it doesn't follow the central limit theorem. It's going to blow past just being able to talk about how wrong we are for sample means. Okay, so this wasn't too many lines of code, but I've got good news for you guys. We can make it less. You don't have to. Like if you write 5 lines of code, nobody's gonna be like, that was way excessive. But there is a way to do this a little bit more efficiently. If you don't follow the more efficient one, that's not a problem, but maybe by showing you the more efficient one, it might give you some cool inspiration or some cool insights. The idea is, if you are told, I've got some samples, from those samples build a PMF, and then pull k new samples from that, we've already seen how you could do that. You could build your histogram, you could normalize it, and then you could loop k times and pull from that probability mass function. Or you could do this. You could say, choose k things from these samples with replacement. It turns out if you don't put this with replacement, you get completely the wrong thing. Actually, going back to this example, if I say I have these 5 things, choose 5 things without replacement, you'll get exactly 2 zeros and 3 ones every time. That's not what we want. Sometimes we want to get 5 zeros, but we want it to be driven by this probability mass function. But if you put replace equals true and I say pull 5 things from these 5 objects, 2 zeros and 3 ones with replacement, the first time it'll choose 1 object from your 5. And the next time it'll choose 1 object from the 5, but it could still be a 0. You could still draw 5 zeros if you pull with replacement. With replacement means every time you take a sample, you leave it in there so that the next one could be that exact same sample. And for those of you who are curious, you could prove to yourselves that this is equivalent to build the PMF, then draw samples from that probability mass function. Draw k samples. So there you have it. A very, very, very fast way of doing the sampling and replacing. Let's talk about how this updates our OG bootstrapping. So this is a bootstrapping we had before. First, you estimate the probability mass function. Then 10,000 times you repeat your experiment. In the experiment, you draw 200 people from Bhutan. You calculate the statistic you cared about, and then you have a distribution of your statistic. So now, I don't know why I have that photo there. Forgive me. But it's very inspiring, maybe because we're feeling inspired. Now we don't actually have to explicitly make the probability mass function. The sample as a list is in fact the probability mass function. And if we choose 200 items from this list with replacement, that's the same as first construct the probability mass function and then draw 200 samples from that constructed PMF. It is equivalent to just pulling 200 things from your original sample with replacement. Now, to be clear, if there's only one of these that you understand, I want it to be this one, because that's where the theory derives from, and this is just the programming shortcut. But if you're really excited to think about why this programming shortcut is correct, I would encourage you to do so, because I do think it will just reinforce some fundamentals, if you're curious. The rest of the algorithm is exactly the same. Yeah?
What are we cutting out? Like, what's the shortcut?
So in the first one, before we do 10,000 steps, we actually construct a physical probability mass function. Yeah, and now we don't have to construct the actual probability mass function. We just keep a list of original samples around, and then we sample from that with replacement. Crazy. Okay? We have to code this. We can't talk about this in theory anymore. We've got to see some code. Are you guys ready? Okay. I have a world for you that's going to put this to the test. I'm going to make a random country, and that random country is going to have 1,000 people in it. And it's going to, when I make this random country, I'm going to know the true variance of the people in the country, because I made the country, and then I'm going to give you a sample of happiness from it. So I know the right answer because I made the country. Don't use this, okay? Just use your sample, and your question is from the sample, can you guess the right answer, but can you also express how wrong you might be in your guess? And so we're going to bootstrap. We're going to repeat 10,000 times. And what are we going to repeat? Bootstrap that var. Yeah. 1. Resample a new group. Recalculate the stat we care about. Now, in this case, we're talking about the variance. So what we should, the stat we care about is going to be the sample variance in this case. Okay, how do we resample a new group? One option would be to say, like, probability mass function equals create PMF from this list of 30 people. And then we could try and pull 30 people from PMF. We could say, take that PMF and give me 30 people from it. That's what we could have done, but I am going to try and use the programming shortcut. In the programming shortcut, instead of doing this, I'm just going to do np.random.choice, and then I'm going to say, take my original sample. From them, we're going to choose 30 people, and replace is going to be equal to true. Let me just print this out. And let's just look at it for one time through the loop. And then we can think about our lives. You guys ready for it? Okay, one time through the loop, I got 30 people. And that's their number. That's great. That's not the end of it. I'm supposed to recalculate the statistics. So in this case, calculate sample variance with the new sample. So I have a function which does what we did on Monday's class. And I'll call that s squared or something. And then I'm going to put that into my list. And now when I run this 10,000 times, I'll end up with a list of 10,000 numbers for my variances. And then I'm going to, I have a little histogram plot of it. Oh, and look at my variances. Isn't that kind of interesting? And once you have this, you can talk about lots of things. I have my whole distribution of variances. I can be, so the true variance was 24.7. My estimated variance using sample variance was 24.6. So I was a little bit off. Well, actually, I was lucky to be that close because, in fact, the standard deviation of the statistic is 6. So you could be really far off. So if somebody reports to you at 24.6, they got a little bit lucky. They could have reported anything from like a 20 to a 30 for this particular number. Okay. So at this point, bootstrapping allows us to get something like this, which says, we can talk about how wrong we were in any statistic we care about. Could be sample variance, could be something more interesting. And really, it allows you to talk about probabilities of statistics using code, and it's a beautiful thing. Quick history, why is it called the bootstrap? Because it's like, the idea of bootstrapping comes from this metaphor of picking one up from your own bootstrap. So imagine you're lying down, and you have to grab your boots to get yourself up. Sounds hard, right? And that's why they call it the bootstrap, is because this assumption that the true underlying distribution is simple or equal to your sample seems as hard as pulling yourself up from your bootstrap. And it's crazy that it works out. And so that's why it gets its name, bootstrapping. And it was invented here at Stanford in 1979 by this guy who's still a professor at Stanford. And he won a National Science Medal for inventing the bootstrap. I don't do celebrity lookalikes for colleagues. So what I did do is I let the internet do it. So starbyface.com gave me somebody I don't know. But anyways, Bradley Efron invented the bootstrap here at Stanford. What a beautiful thing. And it works for any statistic, but there is a big asterisk. Your samples have to be IID, and the underlying distribution has to be one that doesn't have a long tail. So if you guys remember the climate change problem, you explored long tail distributions. For things that are long tail, it turns out that this can break down. Which leaves us with the most important question. I claim that this can answer a crazy important idea in science, which is you made a claim. You had group A, it had its mean. You had group B and you had its mean, and from those two things you calculated a statistic. And that statistic was the difference between those two groups. Can you talk about how wrong that statistic could have been? There's two different ways of talking about it. You can calculate the variance of that statistic, and we could do that in exactly the same way we did before. But I do want to introduce you to this idea of a null hypothesis that's been in the history of science for a very long time. When comparing two groups, people often think about what's the chance of seeing a difference this big if my two groups were the same. The null hypothesis says you had two different groups, but they're not actually different. And any statistical difference you saw is because you didn't do your stats right. No, I'm just joking. It's because you didn't have a big enough sample. And everyone has been calculating the probability of this null hypothesis. The probability of this null hypothesis has a particular name. It is called the p-value. And bootstrapping gives us a very nice and simple way to think about the probability of the null hypothesis. It starts out with this crazy idea. So you have two lists, right? And you want to know how likely it is that this calculated difference in means is meaningful. And the way we're going to do that is we're going to imagine it's not meaningful. We're going to imagine the null hypothesis. In the null hypothesis, you had 20 people in group A and 20 people in group B, and they're all pulls from the same group. There's no difference between group A and group B. You just got 20 samples from student population and 20 other samples in the student population, and you called one group A and group B, and that was totally meaningless. That's the null hypothesis world. In the null hypothesis world, the true probability mass function is the concatenation of the people in population 1 and population 2. So if you looked at the null hypothesis world, if you had these numbers for group 1 and these numbers for group 2, the null hypothesis world is put all those numbers in one big bag, and that's the distribution of students, and you just happen to pull 20 and call it group 1, and you just happen to pull 20 and call it group B, or 2. Questions about the null hypothesis. It's a weird concept. Once you know the null hypothesis, the bootstrapping will come nicely. Have you guys seen this before? Can you nod your heads? You've seen null hypothesis in other classes? Some folks, but it's new for other people. Okay, so the idea is, in the null hypothesis, everything comes from one distribution. You just called this group A and you just called this group B. There's no statistical differences between these IID samples. It's just you pulled too little and you saw a difference in means. So in bootstrapping, here's what we do. We make the universal distribution by taking population 1 and extending it with population 2. I make a list which has all the people from population 1, population 2, and that is the probability mass function of the universal distribution. 10,000 times we bootstrap. And when we bootstrap, we calculate the exact same statistic that we calculated in our science claim. We get a group of people and call them group A, or in this case, group 1. We get a group of new people and call them group 2. And they're all being pulled from the universal population. So 10,000 times, we take random people, call them group 1, random people, call them group 2, and then we calculate the mean of each of those groups and we look at the difference in means. And then we just add it to our list. So we'll add up 10,000 differences in means. You could count how many of them are bigger than your observed difference in means. Some people do that, but I actually want to look at the full distribution of differences in means in this null hypothesis world. So you guys ready for this? Ready or not, here it comes. So 10,000 times we make scientific experiments with group A and group B. 10,000 times we calculate the statistics. This time it's not sample variance that we're calculating. The statistic we're calculating is the difference in sample means. That's a statistic as well. And that statistic, if you look at it, in the null hypothesis, it's very likely that the absolute value of the difference in sample means is close to a 0. Because they came from the same distribution. Those two sample means are very likely to be similar to each other. But even if you pulled 20 samples from one group and 20 samples from another, it's still possible that, if you pull 20 from the same group and another 20 from the same group, it's still possible that they have different means. And we can calculate exactly what's the probability. We can say, using bootstrapping, we know the full distribution in the absolute value of the difference in sample means. And the probability that under the null hypothesis you would have seen a difference in means this big is what is the probability of seeing a number in my distribution greater than the difference you observed. And this probability you can calculate. You have the full distribution. You could just sum up all these probabilities from your probability mass function of your statistic, and you say the p-value, the chance of seeing a difference this big or bigger based on the null hypothesis is 0.008. And if you know the famous science claim, if you have a p-value less than 0.05, it gets accepted into science, which is its own problem. So the idea here, every science result needs a p-value. So a lot of science results are statistics. I had two groups. I calculated their means, and the difference in means, the effect size is 0.7. That statistic, we need to know how bad it is. We could just look at the variance of that statistic, but in science we often look like, what's the probability that you could have seen the statistic assuming your groups were exactly the same? Bootstrapping, what an incredibly powerful tool. It works for so many different questions you could ask. It allows you to use your computer to run 10,000 simulations incredibly quickly to understand distributions of any claim you're making. And if you can understand the distributions of any claim you're making, you can talk about it more probabilistically. It makes this insane assumption, which we're still going to dig a little bit deeper into, which is that a great assumption for your underlying distribution is just the histogram of your samples. Questions before we jump into it? I do have one food for thought to leave you with, though this is the most important takeaway is what I've got up right now. Yes?
Can you just say,
the p-value is the probability that under the null hypothesis, therefore everybody is coming from the same distribution, that you would have seen a difference in means this big or bigger, or whatever statistic you claimed. So I claimed that my difference in means was greater than 0.7. That was my claim. So you would have seen a claim that strong or stronger. Under the null hypothesis, what's the probability of you seeing a claim that strong or stronger? In this case, my claim is the absolute value and the difference in means is 0.7. And you guys will practice this in section. Yes?
How did you make the universal population?
Good question. This beautiful line of code. I could have even done it without the deep copy, but I just want to keep my population around. These two lines of code. I created a list, I put everybody in population 1 in it, and then I added everybody in population 2 in it. That is the universal distribution. Good question. Okay. You guys are wonderful. This is one of the harder classes to follow. And thank you guys so much for working so hard. I tried my best to make it as clear as possible. You will get to practice this in section. You'll look about corgis on islands. It's a good time. Have a fantastic time in section. So wonderful to see you. See you guys back in class on Friday.